Oh. Ah, en YouTube. Bueno, no sé. Bueno, después te digo. Después te digo. Vale. Vale. Sí, yo aviso. Yo aviso.
Boa tarde a todos. Sejam todos muito bem-vindos a mais um seminário do Grupo de Dinâmica, Orbital e Planetologia de Guaratinguetá. Hoje a gente tem o prazer de receber o José Davi Gutierrez. Você é estudante de pós-doutorado da Universidade de Saragoça, na Espanha, e ele veio passar 2 meses aqui com a gente num sanduíche dele, né, para trabalhar com alguns professores nossos aqui do grupo, Alessandro e André, né? E hoje ele vai falar para a gente um pouco sobre essa questão da estabilidade, né, da órbita, da dinâmica orbital ao redor de asteroides. Obrigada, você.
Thank you very much. Can you hear me? People from online can hear me? Yeah, okay. So in this presentation, I would like to talk about what I'm currently working on my thesis. So this talk is called Orbital Mechanics around non-homogeneous elongated asteroids. And it is about applying results and techniques from dynamical systems to the study of the motion around So I would like to begin with a little bit of motivation. Asteroids are small, rocky, celestial bodies that are found in the solar system. Although they can have many shapes, elongated asteroids are quite common. For example, here we can see Cleopatra or Eros 433 or Haida that has an elongated shape. Not also they are elongated, but they are irregular in terms of mass distribution and composition. For example, Cleopatra has these lobes at the ends of the asteroid, right? So what we are going to do is to investigate how these irregularities affect dynamics around the asteroid. Okay? Okay, so how does a small particle or a small object move around the asteroid? Well, we start with this general expression for the Lagrangian. With the Lagrangian, we obtain the equation of motions. Here, W is the gravitational potential of the asteroid. So we obtain the equation of motions, and these kind of systems are conservatives, okay, which means that this quantity here is preserved along the orbit, and it's called the Jacobi constant. Okay, but we need to know the expression for the gravitational potential of the asteroid, right? Because these are just equations in general. How do we compute the gravitational potential of asteroids? Well, there are two main approaches. The first one is called the polyhedron model, where the asteroid is modeled as a polyhedron with many faces and vertices, and compute the gravitational potential like that, okay? It's a very complicated formula, but another approach is the mass concentration model, where the asteroid is supposed to have many tiny particles. I don't know if you can see from here, but the asteroid is composed of many points, which gravitational potential is just this. So the total gravitational potential of the asteroid, the total gravitational potential of the asteroid is the sum of the potential of all the points. Okay, so these two models are quite realistic, and when you plan to do some space missions, for example, if you want to send a spaceship to an asteroid to land on an asteroid, you want to compute the gravitational potential as precise as possible. However, this has an inconvenience that these models are computationally expensive. And for the kind of study that we want to do, which is a qualitative study, this is really bad because we need to compute many times the potential at some point. So we want it to be fast. What do we do then? Okay, we can simplify the shape of the asteroid. For example, here we have Psyche, and we can assume that Psyche is an ellipsoid, right? Which has a simpler gravitational potential, and of course going to be faster in terms of computational time. But also this has another advantage, which is that if the model is simplified enough, we can apply theoretical results from dynamical systems. Also, these kind of models have fewer parameters, and we can play with those parameters to see how they affect the dynamics. And of course, they still have a similar qualitative behavior. The question now is, how do we model or simplify the model for a elongated asteroid? One approach is to look at the geometry of the asteroid. For example, Cleopatra has this neck and two lobes at the ends, right? So we can simplify the asteroid as a segment with 2-point masses at the ends, right? So this is after looking at the geometry of the asteroid. And this model is called the dipole segment model, okay? Because it has a segment, and these 2 points are called poles. But the approach we are taking in this work, which is a new approach, is to look at the internal density distribution of the asteroid, because it has been shown that some asteroids doesn't have a constant density. For example, this is an estimation of the internal density of Eros. Okay, so what we're going to do is to assume that our asteroid is just a segment without these poles, okay, but with variable linear density, okay, and see how this variable density affects the dynamics. Well, let's build the model, okay. Suppose that our asteroid is a segment with mass m, with total mass m. The asteroid is a linear segment. I mean, here I'm showing the asteroid with a little bit of volume, so you can see it. But in the model, the asteroid is just a one-dimensional segment. Okay. Also, since it's very rare to find and completely static asteroids in the space, they are usually rotating. We are going to assume that the segment is rotating in the xy plane with constant angular velocity, omega. Okay, so the asteroid is rotating like that. Okay, with being the zeta axis is the axis of rotation, and the origin is the center of mass of the asteroid. And of course, since we can always make a change of variables so that the units of distance are the length of the asteroid, we are going to assume that the asteroid has length 1, okay, for simplification. The last thing and the most important thing is the density. The asteroid is, the segment is going to have a linear density sigma, which has a form of a polynomial of degree 2. Why a polynomial of degree 2? Well, we could have chosen any other function. But for simplification, we have chosen a polynomial of degree 2, which is represented here as a red line, okay? So in this case, for this example, the center of the asteroid is less dense than the ends of the asteroid, okay? One thing to notice is that the constant term in the density is chosen so that the total mass of the asteroid is m. So we have three coefficients, A0, A1, and A2, but A0 depends on A1 and A2. So we only have actually two free parameters, A1 and A2, that controls the curvature or the mass distribution of the asteroid. Okay? So with all of this consideration, we have this expression for the gravitational potential. And you can say, okay, this is a simple model. Yeah, it's simple, more simple than using the polyhedron model, for example, or the mass concentration. Here, R1 and R2 are the distance to the ends of the segment. Okay, so we can write our gravitational potential in terms of the distance to the ends of the segment. But this is the gravitational potential of an static asteroid. We have said that our asteroid is going to be rotating. So if we put a rotating frame of reference such that the origin is the center of mass of the asteroid, and the asteroid is aligned with the x-axis, we obtain this effective potential, which is more or less the same as the restricted three-body problem, right? Where you have the primaries, but you have a rotating frame of reference in the center of mass of the primaries. So this problem is more or less the same, but instead of two bodies, you have just a rotating segment. Again, this system is conservative, and we have this equation of motions. Once we have the equation of motion, now we have defined our dynamical system. So we have the flow. It's just the mapping that for every initial condition given by position and velocity. The flow at some time t is the solution of this differential equation, starting at this initial condition and integrated up to time t. And we call, just for refreshing concept, we call the orbit of P as the trajectory followed by P with the differential equation. And now that we have our dynamical system, we can study the typical things of dynamical system, which are equilibrium points, periodic orbits, and so on. Okay, let's start with equilibrium points. Equilibrium points are points in the phase portrait that aren't moved by the flow. So the differential equation evaluated at those points is 0. So this system, the variable density model, has always 4 equilibrium points. 2 of them are called L1 and L2, are the collinear equilibrium points because they are in the same axis as the asteroid. and they are always unstable, independently of the parameters. Also, they are unstable, but they are of the type of a saddle center, which means that around this equilibrium point, although they are unstable, there is some region in which orbits behave cyclically. We will see that later, okay? But we also have two equilibrium points, L3 and L4, which are called the triangular equilibrium points. And the stability of those equilibrium points depends on the parameters, depends on the mass distribution parameters. Recall that this was A1 and A2 were the density parameters. And also in this quantity here that relates the angular velocity and the mass of the asteroid. So this quantity here, K, omega squared. This quantity here also affects the stability of the triangular equilibrium point. If they are stable, of course, they are centered. But when they are unstable, they are a complex sink and a complex source. So around these equilibrium points, when they are unstable, orbits behave like a spiral. We will see that later too, right? Okay, but let's see a little bit more about the stability of the triangular points. Because as I said before, it depends on this constant K and the density distribution. So here we have plotted the stability of the equilibrium points for some values of K, of the constant K, for all the values of the mass density distribution. So this means, so this shape here you see, okay, is the set of all A1 and A2 coefficients that leads to a positive density, because we can't have negative density. So actually, we can't use any value for A1 and A2. We can only use values that have positive density. So this shape here is what it means, okay? And in red, we have plotted, in red is where the case is, where the equilibrium points are unstable, and in green, where they are stable. So we start with K equals to 1, and we see that for every density distribution, the triangular equilibrium points are unstable. But as we increase the constant K here, for some values of density distributions, the equilibrium points become stable. And up to K equals to 10, where almost for all the cases, the triangular points are stable. But there are two things to notice here. First one is that concave density becomes stable before convex density. So concave density is when the density is just like that, and when the parabola is something like this, and convex density is when the parabola is something like that. So the concave density region corresponds to negative values of A2, which are more or less here. As you can see, as we increase the K constant, this region becomes stable, while this one remains unstable. So actually, concave density is more stable than convex. And also, asymmetric densities becomes stable earlier. Asymmetric densities are represented in those regions here, in the sides of this weird shape. Okay, so symmetric density is in the center, and asymmetric densities outside the center. And we can see here that they become stable earlier than symmetric density. Okay, another thing to notice on this model is that they are reversible. Here we have the formal definition of reversible, but the general idea is that a system is reversible if there is some symmetry that is equivalent to go back in time. So if we have a reversible system, it's the same as integrate the initial condition P forward in time as make compute the symmetric of this point, go back in time, and then compute again the symmetric of this point. Okay, so it sounds complicated, but in reality, in our model, the symmetry is this one. So if we change the sign of the y-axis and the velocity in the x-axis, it's the same as if we go back in time. And the set of all symmetric points is the x-axis, okay, y equals to 0, which is the x-axis, with initial velocity perpendicular to the x-axis. So, yeah, you have to consider that initial conditions have 4 dimensions. So, I don't know where to write this. Okay. So, the set of all initial conditions that start here and perpendicular to that, or like that, are symmetric. And as a we can also have the triangular equilibrium points are the symmetric one from each other, right? Because they are both at the one side of the x-axis. So we have explored the equilibrium points and some properties of the variable density model, and now we are going to study the periodic orbit. Just to refresh, we say that an orbit is periodic if after some time t, starting at some point p, after some time, the orbit actually crosses again the initial point. For example, this is a periodic orbit, right? Because after some time, we get back where we started. In Hamiltonian system or conservative system, that the one we have, periodic orbits appear in continuous families, okay? So this indeed is like a continuum, like a disk, okay? But I only represented some of them. Also, it's possible to parameterize these periodic orbits by the Jacobi constant. So, locally speaking, each of one of these orbits has one value of Jacobi constant. So, if you move along the family of periodic orbits, you change the value of the Jacobi constant. Okay, but we said that we have a reversible system, and periodic orbits in reversible system verify a very interesting property, and it is that if a point P is symmetric and the trajectory of P after some time is also symmetric, then the orbit passing through P is periodic. What does it mean? Is that we have a symmetric point here, and we start integrating. Okay, start integrating, and the trajectory crosses again the symmetry axis. Okay, then we have a periodic orbit that does the symmetric of the trajectory you did. in our problem, since we have a particular symmetry, which is reflecting the y-axis and the velocity in x-axis, this means that if we start perpendicularly, whenever we, in the x-axis, whenever we cross again perpendicular the x-axis, we have a periodic orbit. So here, for example, you start integrating, you cross the x-axis, but it's not perpendicular, so here yet we don't have a periodic orbit. You keep integrating and find that at this point you cross perpendicularly. So now you know that you have a periodic orbit that does the symmetric trajectory. Okay? So we only have to compute half the things. What when you have a reversible system, planar symmetric periodic orbits can be represented in the plane. Why? Because since it is symmetric, the initial condition must be in the x-axis and start perpendicular to it. So why is the initial condition y and the initial velocity in x must be 0. So you have two, let's say, three components of the initial condition, which are the x0, the initial value of x, and the initial value of the velocity in y. But in the literature, they are usually represented or interchanged, better said, with the Jacobi constant, because we said that the Jacobi constant is a natural parametrization of families of periodic orbits. So we usually change the value of the velocity in the y-axis for the Jacobi constant. So a family of periodic orbits can be represented as their initial conditions in the x0 and z plane. And these are called characteristic curves. So for example, this curve here is the representation of the initial conditions of a family of periodic orbits. So we can let's search all the periodic orbits you have in a system by computing these curves. Okay, so because since each of them represents a family of periodic orbits, you can scan all the values for x0 and all the values of z of the Jacobi constant and obtain all possible initial conditions for periodic orbits. Okay, now we are going to compare the families of periodic orbits in the variable density model, and we need to set the parameters we are using. So we are going to compare two densities. What happens when we have a convex density like that and a concave density like so? Okay? In both cases, we are going to take the gravitational constant times the mass equals to 1, and the angular velocity of the asteroid also as 1. This makes the triangular equilibrium points unstable, okay, always. That's why we have chosen those values. And for the convex density, we have chosen this parabola here, and for the concave density, this one. So these are the characteristic curves of the convex density model and the concave density model. All these curves here represent families of periodic orbits. As you can see, there are more families in the concave density model than in the convex density one. Actually, some families are the same in both models. For example, this one here is the same as this one. Okay, so every family that appears here is marked as with the same color as families appearing in the concave density because they are the same family. The only thing is that they change a little bit the shape. as we will see it. So let's see how is the shape of those families. For example, the red family, this one here, okay, in both models, correspond to this family of periodic orbits. Recall that periodic orbits appear in a continuous way, okay? So this lighter color means that there is a continuum transition from this orbit to this one, right? But if I plot everything the same color, we cannot see anything, okay? So here we can see a little bit the shape. For the red families, called the family M, they have more or less the same shape, so doesn't change. But when we look at the blue family, the family L, which is this one, okay, this one in both models, now we see some changes because this family starts far from the asteroid, and as it gets closer, in the convex density model, it does some kind of spiral around the triangular equilibrium points. Remember when I said that when the triangular equilibrium points are unstable, they have some spiral behavior around them? That's what's happening here. The periodic orbit is trying to follow this spiral behavior around the equilibrium points and ends up converging to them. But in the concave density, it doesn't happen. It starts far from the asteroid and ends up connecting the collinear equilibrium points. The same happens with the Lyapunov families. Lyapunov families arise in the collinear equilibrium points and get far from them. So in the convex density, they also tend to spiral around triangular equilibrium points. The same with the other the symmetric Lyapunov family. But in the concave density, this behavior is lost. So we don't have this spiral behavior around triangular equilibrium points. And lastly, last of the common families between both models is the family K, which starts very close to the asteroid and ends up doing this spiral behavior around the equilibrium point, which doesn't happen in the concave density. So these are all the families that appear in the convex density. We have 5 families, okay, red, blue, orange, green, and purple, and also appear in the concave density model. But here we have some new families that doesn't appear in the convex density, and those are this family. So for this family here also have a spiral behavior around triangular equilibrium points. So this behavior doesn't disappear for the concave density. It's just that another family inherits this spiral behavior. Well, these are all the families we have found. And now let's talk about stable and unstable manifolds. In dynamical system, when you start studying them, you usually see equilibrium points, periodic orbits, but these kind of objects, objects in dynamical system, is also very important. And a stable manifold of an equilibrium point is the set of all trajectories that converge to the equilibrium point. So here, the stable manifold of the equilibrium point P0 is the set of all points that, after making the time goes to infinity, the trajectory ends up in the equilibrium point. The same happens with the unstable manifold, which are the trajectories that start in the equilibrium point. So it's all the trajectories that when the time goes to minus infinity, goes to the equilibrium point. So it's actually, as is the trajectory connects the equilibrium point to the outside of the equilibrium point. Right? You can think about this stable and unstable manifold as highways to connect the equilibrium points to the phase portrait, because they come from every part of the phase portrait and ends up in the equilibrium point, and vice versa. They start near the equilibrium point and they go away. And also we have this theorem to approximate the stable and unstable manifold, that we can use the linearized system to compute this manifold. So for example, I'm going to draw here. You have an equilibrium point, and you study the local behavior, and for example, you obtain a saddle. So you have one trajectory like that the orbits go away like so, another trajectory like that, and no, like that, no, like that. Sorry. Like so. So this is the local behavior of an equilibrium point. Orbits nearby this point do something like that, right? So if you start here, if you start at this point here and propagate the orbit that goes away from the equilibrium point, you start computing the unstable manifold, okay? Because this trajectory, when time goes to minus infinity, reach the equilibrium point. And the same with the stable manifold. You start here, and your trajectory ends up in the equilibrium point. So when you propagate back in time, you obtain all the stable manifold. Okay, let's this is very theoretical, but here we can see those manifolds, right? We have the blue one is the stable manifold of the L1 collinear point. The red one is the unstable manifold of this point, and this dotted line are just the stable and unstable manifold of the linear system. So you can see they are tangent, so you can approximate them by the linear system. Also, we have a reversible system, so there is some kind of symmetry that make our job to compute this manifold easier. Because if we have a reversible system and we have two equilibrium points, one of them is the symmetric of the other equilibrium points, then the unstable manifold of one equilibrium point is minus the symmetric of the stable manifold of the other equilibrium point. As we see here, this is the stable manifold of the equilibrium point in our model, of the triangular equilibrium points in our model, and this is the unstable manifold of the symmetric equilibrium point. So you can see that actually there is some symmetry, right? Because it's like if we reflect the manifold. As a side note, stable and unstable manifold can also be computed for periodic orbits, okay? So the stable manifold of a periodic orbit is the set of all orbits that ends up converging to the periodic orbit. And the same with the unstable manifold. Right here we see some example for the convex density model. These are all the red trajectories are all the trajectories that start orbiting very similar to this periodic orbit, but then go away. And the same with the stable manifold here. Now, the question is the following. We have orbits that converge to an equilibrium point, orbits that diverge from an equilibrium point. Is it possible for an orbit to go for one equilibrium point to other equilibrium point? And the answer is yes. We have something called heteroclinic orbits. They are orbits that goes from one equilibrium point to other equilibrium point. So they are something like this. You have two equilibrium points, 1, 2, and the orbit does something like that. Okay. We can also have homoclinic orbits, which is the same, but for the semi-equilibrium point. So it starts in an equilibrium point and goes to the same equilibrium point. So this is heteroclinic orbit, and this is homoclinic orbit. How do we find those kind of orbits? Well, very simple. The heteroclinic orbit is in the intersection from the heteroclinic orbit from one point to other is in the intersection of the unstable manifold and the stable manifold of those equilibrium points, right? Because these are all the points that goes to the equilibrium point when times goes to minus infinity, and these are all the trajectories that goes to the equilibrium point when the time goes to plus infinity. So in the intersection, we find those kind of orbits. And the same with the homoclinic orbits. They are in the intersection of the unstable manifold and the stable manifold of the same equilibrium point. And one comment, because with this drawing here, you can get some intuition, but things from here, things can get really, really weird. Because, you know, for example, the function sine of 1 over x. You know that function, right? That oscillates infinitely many times between -1 and 1, right? in a bounded interval of x. Stable manifolds and unstable manifolds can fall like that, can behave like that. So when you compute the stable and unstable manifold and their intersection, you arrive to this kind of problem where they intersect infinitely many times in a in a dense way. So you can have infinitely many heteroclinic and homoclinic orbits. They are very similar to each other, but yet a little bit different. So when this happens, we have chaos, right? So that's happening in our model. This is very common when you have nonlinear system. And I just wanted to make this comment. So here are some examples of heteroclinic orbits for the convex density model. The blue ones goes from L3 to L4. So there are two. This goes from here to here. And the other one goes from here to here. Okay. And the red ones goes from L4 to L3. Of course, if we have a reversible system, heteroclinic orbits appears in pairs. Okay, so if you have this blue one, as your system is reversible, you also have this red one. It's the symmetric of that. Okay. So, and this one is for the concave density. As you can see, pretty different. So it's also something that depends on the internal density of the asteroid, the heteroclinic orbits. Some examples of homoclinic orbits, and what I'm saying, and why am I saying some examples and not plotting all of them? Because computing these orbits are way more complicated than the heteroclinic orbits. Because with the heteroclinic orbits, you can use the symmetry of the system, right? Your system is symmetric with respect to this axis. So it's faster to compute heteroclinic orbits, and you can compute all of them. But here, the method is more complicated because you have to exploit the symmetry with respect to the y-axis. But this orbit, since it is spiraling around this point, crosses infinitely many times the y-axis. So sometimes you get all the orbits, the homoclinic orbits, sometimes not. But one thing to notice is that these two orbits, these two homoclinic orbits, for example, they are very similar to each other, but they different just a little bit, and yet the initial condition differs just a little bit, and yet you have completely different behavior. Okay, but still they have some common feature like this weird loop here, right? But they are completely different. Also, since you can have a stable and unstable manifold of periodic orbits, you can also have heteroclinic orbits between periodic orbits. So this one are for the convex density model. This one for the concave density. But then it is harder to make a study on them because you have infinitely many periodic orbits here. And also, for each periodic orbit, you have one or more heteroclinic orbits. So it's virtually impossible to compute all of them. And just some explanation, some relation I want to clarify between periodic orbits and heteroclinic orbits. Because in reversible Hamiltonian system, we have this theorem that says, for every pair of heteroclinic orbits connecting two non-symmetric points, there is a family of periodic orbits converging to them. So remember that in the convex density model, we have this family, right? That was doing some loop around here. What's happening is that this family is converging to the composition of these two heteroclinic orbits. That's why the characteristic curves were doing some kind of spiral, because the family of periodic orbits were converging to the union of the heteroclinic orbits. And I don't want to make this presentation any longer. So I would say that the most important conclusion of this work is that internal density of asteroid actually affects the dynamics around them. It's a really important thing to consider also, the internal density. Here are some references, and that's all. Thank you.
Thank you.
Thank you.
Any question?
Thanks for the presentation. I think you must be a very good teacher. You explain very carefully and very clearly. I think I do not have any specific question for the work, but I was thinking on other approach, other applications. You discussed about having a parabola with different concavities, but if you have just half parabola, you know?
You mean like an asymmetric
your object,
parabola?
Your object has just half of the shape. So you have one concentration on one side of the more dense and goes
like that.
Yes. Or
that's also a thing to consider. For the moment, we have only considered the variations in convexity, but it's also an interesting study to see variation in symmetry, because as we saw before, asymmetric density are also more stable. So I think that you can have more variations here too. Yeah, that's an interesting problem
Yeah.
to investigate, but yet we haven't done anything on that.
There are some shapes that this would apply. I think would be you have on like a one
Yeah,
extensive. One side is more dense and then goes like that.
For example, no, this one, no,
Yes, yes,
very asymmetric.
that's right.
Yes.
That's
And
right.
part of my work here with Alessandra, Andrea, and other students is trying to fit this model to real asteroids. So we know if the density is more asymmetric or more symmetric, and so. But yeah, it's a very interesting problem.
Good. And I have also another suggestion of work that would be to use Poincare surface of sections.
Yeah.
You have everything fits on that.
We have only done some tests, but not a rigorous comparison between them. But yeah, we are planning to compute also Poincare sections.
We have done some use of Poincare sections for different problems, and because usually people look for the periodic orbs and focus on that. And I see another kind of application. We have done some work on when you have the periodic orb, you have a quasi-periodic orbs around it. And the width of this region, and you have, let's say, islands of stability and chaotic regions in between. So sometimes you can identify the size of these islands, and that would be important for a space mission, for instance, where to put your spacecraft. And so the surface of sections, they bring something else that not just the periodic orbs. I think you can compare. But what I'm saying is that it's more powerful in the sense you can identify the chaotic regions, the location of them, and the quasi-periodic orbs. Because if you have, let's say, you have a stable periodic orb, and you have quasi-periodic orbs in a wide island, so you can, let's say, you have an arrow bar much larger for the spacecraft to be inside that. And when you have it's narrow, even being stable, it's dangerous because you may be moved. So sometimes when you study just the periodic orbit or one equilibrium point, you have the linearity of the study is mainly in the near neighborhood. And so the Poincare surface of section offers the opportunity for you to have the size,
view,
the size of the neighborhood much larger or smaller. So and it applies for this problem. I think it would be very interesting.
Yeah. I think that is interesting too. That to compute Poincare sections of some periodic orbits. But this is part of a continuous study. So we have yet to do a lot of work to do. But thank you very much for
your presentation was very good. So I think I understood most of it. So I do not have much questions. So I was thinking on something else could be done. Congratulations.
Thank you.
I think Sylvia wants to make a question. Ela entrou? Não?
Não, Rosana, obrigada.
Okay, Sylvia. Any other question from people here or from Google Meet?
André.
André?
Hi, José. Thank you for the presentation. I think just one suggestion. I think that the convex shape, when you think when you talk about that, you can use it and maybe binary systems because the density between the bodies is very you don't have, okay? And also the another convex concave, you can use it in systems like Cleopatra, maybe or system, you have between the lobulus a high density, something like that. So I think binary system is very interesting because you have 4 equilibrium points, for instance, because in another depends on the shape of the body. So depends on the shape of the body, you can have like 8, 9 equilibrium points. So binary systems, I think, fits very well in this
Yeah.
this work.
Thank you.
Yeah.
Any other question, Isabel?
Congrats for your work. Maybe it's my physicist point of view, but do you need to consider the gravitational force in your accounts?
Sorry,
Gravitational force.
of the satellite.
Yeah, especially when you study the orbit of the family asteroid group, you know.
I didn't understand. You need to consider the gravitational force.
Yeah,
of
when you study the family
the
group.
family tree.
Yeah, I don't know. It's not my.
No, well, we have just supposing that the satellite that is orbiting the asteroid is just a particle. So it doesn't influence the rotation and orbit of the asteroid.
Yeah.
Of course, you can this model more realistic by doing so. Also, you can include more perturbation like solar radiation pressure and so. But yeah, that complicates the equation and makes it harder to investigate. Right? But yeah,
Gotcha.
it could be possible to implement too. Yeah.
Okay, gotcha. Thank you.
Jose, we have a question from people remote. Maísa?
Yes.
Maísa, can you hear?
Maybe. It's,
Now, I think that now.
now it's
Okay, thank you. Excuse me. I would like to know if you investigate situations where the body is not symmetric, or the shape or the distribution of mass is not symmetric, because in this case, I think that the triangular points will be not symmetric one to the other, or something like that.
yes. In actually in this paper here, in one of the references here, in this paper here, at the end, we compare the convex density to the dipole segment model for an asymmetric density distribution. But we haven't examined yet a systematic comparison between asymmetric and symmetric densities. So this study was also, we computed some periodic orbits for an asymmetric convex distribution, but this work is more about compare the different density distributions. So we haven't studied it yet systematically. I don't know if this answered.
Yes, thank you.
Thank you.
Any other question? Yeah. I do have a question. Have you ever compared your results with your model with another model, such as mass cones or?
With a realistic model, no, and that's why I'm here. I'm here with Alessandra and Andre to learn how to use realistic models, because they it's possible to do some fitting on the parameters, so you can obtain the best parameters in your model to replicate the gravitational potential of asteroid. We have only do this comparison with the dipole segment model, which is other simplified model, but not with a realistic model. Yeah,
Okay.
that's it.
Any other questions? No? So let's thank again José David. Thank you.
Thank you too.
Silvia? Sorry, Silvia.
Não, apertei errado de novo.
Ah.
Desculpa. Eu ia aplaudir e apertei errado.
Tudo bem. Thank you. A lot of people congrats you.
Thank you very much.